Welcome to the video recording of type providers in F# for Xamarin University. My name's Glenn Stevens and I'll be taking you through today's course. Before you begin, there'll be a number of exercises that we'll be going through, so you should download the class materials from university.xamarin.com before we get started. Okay, let's get into it. In this class, we're going to learn about how to consume data in an F# application using a highly customizable feature called type providers. And we've got two objectives that we're going to cover today. First, we're going to talk about type providers and how to connect to data sources. And then next, we'll look at query expressions, which are often used with type providers to filter, select, and transform data. Let's start by looking at what type providers are and how to use them. And we'll be looking at how to define type providers, how to explore the benefits of type providers, and also how to connect to different types of type providers too. And we live in a data-rich world, and more information is available and around that users will have access to and consume. However, in most programming environments, consuming external data sources requires a bit of setup and processing independent of the actual work that you typically want to do with the data. And this is because most statically typed languages are data sparse. They often have to do a significant amount of work to even access the information that they need. For example, for most data, you would have to connect to the data source, read the data in some format, push that data into some object representation for your program to work with, and then finally pass that data into your actual custom logic for processing. Now, often many of these steps are manual and they can both complicate your program and introduce subtle issues, particularly when the code is copied from program to program, or so-called clipboard inheritance. In F#, we can omit a lot of that repetitious loading and passing code through the use of type providers. And a type provider is a standardized way to pull data into your application in the form of types, properties, and methods, and takes the place of each of those preliminary steps, allowing your F# code to focus on just the processing logic. And it turns out that most information sources actually have really rich metadata associated with them, which we often use as humans to understand the data. And F# actually pulls that metadata into the system and then uses it to create a much richer way to interact with the data and provide better type information for the tools. And if we peek under the hood a bit, you'll find that the type provider actually has three goals. First, it provides design time information to the compiler and IDE or REPL, and this allows the tooling to provide full IntelliSense for the data structures being managed by the provider. F#'s compiler system's also extensible, and the type provider plugs into this extensibility so that when the compiler hits a type it doesn't recognize from the source code or from reference libraries, it checks with the loaded type providers. And this allows the type provider to inject dynamic types into the compiler's table of known types. Finally, because of this type injection, type providers actually enable static typing for the data being surfaced, similar to the way the dynamic language runtime works. Except this type information is surfaced at both compile time and runtime, so we get compile time checks to ensure the data we're accessing is available and correctly named. And there are a number of type providers for all kinds of data, and it's a thriving extensibility point for F#. And this is by far one of the coolest extensibility points for F#, and a lot of companies and individuals have built type providers to consume their data. And here's a small sampling of the types of data that you can process with F# through a type provider. We also have support for common data formats like XML, CSV, SQL, and JSON, as well as type providers to query online data sources like Twitter, Freebase, Facebook, and the World Bank. And the key benefit here is that the type provider enables rich data discovery through the use of metadata. This data can also be accessed by the F# compiler and allows various IDE features such as IntelliSense and inline documentation with schema and metadata pulled from the data source on demand. And that means you actually get IntelliSense for the column names of the loaded CSV file and have type properties for your Facebook information. Now, say you have some arbitrary data that you'd like to work with, and perhaps it's a spreadsheet. And let's also assume there's some way to retrieve the shape of this data, either infer it or read some metadata that describes it. And that means you know the types, so it's a double rather than a string. You know the relationships, so this column means salary, and possibly some high-level descriptive metadata, like this sheet is for the June 2010 budget. A type provider is a piece of code, often included in a DLL, which has some attributes applied to it that make it known to the F# compiler and toolchain. And when the compiler hits use types in your code that it doesn't recognize, it consults with the type providers to determine how to work with them. And this information allows for static typing of dynamic data, making the data look like real types to the IDE and compiler. And to access the type provider, your code simply needs to add a reference. And there are two supported models that type providers can work with. First, it can be a synthetic type provider where there's no generated code underneath the data, and everything's being synthesized by the type provider as expression trees, using the shape of the data as the guide for the type. Some data, however, has existing code generators such as WCF or Entity Framework, which already creates reasonable types from the data. And in these cases, the type provider can use a more generative approach where it dynamically generates IL or shells out to the tool under the covers to create intermediate files, which it uses to provide the type definitions to the compiler. And the cost for these type providers is that someone has to write the library. And many providers are very general, so one that speaks OData or XL or WMI. And so a handful of type provider libraries makes vast quantities of the world's data available in your programming language with static typing and first-class tooling support. So this tight integration with a compiler and IDE means that you get an unprecedented ability to explore the data while you're writing the application. And F# exposes the type information directly through IntelliSense. And here you can see tables from our SQLite database exposed as strongly typed entities in F#. So you might think, what's the big deal? Entity Framework and Link to SQL can do that today. But the difference is that there was no import from the table or generation of a set of EDMX files or class constructs to map the tables and relationships. And this is data that's live coming from the type provider based on the current schema as it is right now on the database. And if the schema is changed, then my IntelliSense would change with it and possibly cause errors that show up at compile time. So compare that to the Entity Framework, where schema changes wouldn't generally be detected until I tell the designer to requery the schema, or more likely when I try and run the application. So you're probably already sold on using type providers just from what we've talked about so far, but there are two mainstream benefits that we get from using them to access our data. First, our code will be simplified because we have less code to manage and write. And second, type providers are designed for scalability and for performance. So let's take a look at both of these goals in more detail. And type providers make our data access code much easier to work with. First, it's standardized, as you'll see the mechanics for accessing the type provider and its data is the same, no matter what kind of data that you're going after. Second, you don't have to deal with any generated files. Even in the generative case, the files are not directly surfaced to the project or programmer, and this means less source files for you to manage, less files to compile, and a simpler project structure. Type providers are designed to be scalable, and the data returned is always in the form of sequences, which are based on the IEnumerable interface. And that means that the cost of pulling the data out of the provider is incurred as it's consumed. And this allows for massive amounts of data to be exposed without necessarily loading it all in for once for processing. As an example, Freebase, which is a free database of tons of data, has millions of types available and is exposed through a type provider. And we'll actually use Freebase in one of the lab exercises. In addition to relying on lazy evaluation, the abstract syntax trees, which are created to describe the strongly typed data, are created from expression trees. And that means that the F# language can push some of the filtering and processing operators right into the data source where applicable. For example, skipping records could be implemented differently in a CSV file rather than a database to optimize the retrieval of those records. And because the type provider system is integrated into the F# toolchain, it turns out that we can use type providers to access data in the interactive environment as well, either through script files or through the REPL. And this is exactly the approach that we'll need to take in the lab in just a moment, but let's first talk about how to get access to the type provider. First, you'll need to add a reference to the DLL containing the type provider, and the most common set of providers are part of a DLL named F# data. And this library includes the CSV, HTML, JSON, and XML providers, as well as the Freebase and World Bank providers. And you add it to your project using NuGet. So just search for the F# data and you should find it online. And this is an open source provider, by the way, so you can go through the source code on GitHub if you'd like to see how it's implemented. And once you have the DLL downloaded, you need to add it to the project. And this involves one or two steps. For an executable project, you simply need to use the open keyword to make the types accessible to your code. And if you're using the scripting environment, then you also need to add the reference to the runtime using the #r directive. And we've talked about this before, so it's nothing new, but it's worth realizing that the NuGet package isn't added automatically to scripts. And once the DLL is loaded and is in place, you can start to use the type providers contained within it. And all the type providers are created with the same basic syntax. You define a type alias for the provider and provide various configuration flags known as static parameters in angle brackets. For example, if I wanted to use the SQL data provider, I could create a new type called SQL, which is defined by the SQL data provider with the parameters connection string, database vendor, and resolution path, which is the folder location to look for vendor-specific types, and also a flag to always return default values for nullable columns rather than using option types. And these parameters will be different for each provider, but will often include some connection string identifier or location, as well as configuration flags for how to pass the data. So as an example, here's some code showing the CSV type provider. And CSV files often come in a couple of different formats. And one popular format is where the file itself defines the columns on the first line, providing the metadata necessary to interpret the information. In this case, you can provide the file name or URL of the data to the sample static property, and the type provider will then read a set number of rows, controllable by the infer rows property, which defaults to 1000. You can also change the default separator from a comma to some other character, and here we're using a semicolon. And the type provider in this case will open and read the first 100 rows of the stock data file using a semicolon as the separator. And the 100 rows will then decide the type for each column, whether it's a string, a date, or a number. And then the provider will expose the data to the program through type properties using the column names from the first line as the property names. Now, another variation on CSV files is where the column names are known to the program and not included in the file itself. And in this case, you can tell the type provider that the file doesn't have a header line and then provide the proper metadata through the schema static property. You can give it both a name and a property type as shown here, or just the name, in which case the column type is decided by reading the first 1000 rows. Now, the XML and JSON type providers work in a similar fashion. You supply the file to a static property, and then the provider reads the data to decide the property names and types. And again, the interesting thing here is that the type provider reads this information at compile time, and you'll get full IntelliSense on the property names. And then once the provider has been created, you can access the past data through some provider-specific method or property. And many providers use a data context paradigm, providing a getDataContext method that returns an object used to access the data. So regardless of how the data is accessed, it'll have properties and methods which allow you to access dynamically generated types from the provider, all with IntelliSense support. And here you can see two examples. The first is the SQL provider where we pass in things like a connection string and a table name. Then we retrieve the data context to access the table rows. And the second uses the CSV provider to load some financial data from Yahoo, then calls load to load that same URL and retrieve the stock data for Apple Corp. The data retrieved is fully type safe and using the metadata either identified from the data source itself or passed to the provider. And here you can see a loop being run over the rows from the CSV stock information. The act of running the loop causes the provider to read through the CSV file, returning each line as a row. And in this case, the provider only passes the row out if you process it, so not all of the rows are loaded into memory. And this allows for very large data sets to be manipulated, assuming of course that the processing code itself doesn't keep all of them in memory. And the key thing here is that the property name used on each row are specific to the CSV file, the date, closing price, and open price for the stock. And this is very similar to the dynamic language runtime's capability of synthesizing types on the fly, except this is done at compile time and is fully checked by the compiler. And if you mistype a column, the compiler will catch the error before you even get a chance to run the app. So here's another example. We retrieve the data context from our SQL provider and then access the tasks table, printing out the title and his completed columns. And again, by executing the loop, the type provider will begin consuming the data, in this case creating an appropriate select statement and then pulling back each row to process. So let's move on to the flash quiz. Question 1. Which phrase best describes a type provider? A. An intelligent mechanism to bring in types from an external data source to your code. Is it B, an expression which is evaluated on the final line of the function, or C, non-scalable database access? And the answer is A. It's an intelligent mechanism to bring in types from an external data source to your code. Question 2. What command do you use to get access to a type provider in a script file? Is it #O, #R, or #T? And the answer is #R. Question 3. Type providers tend to be scalable because they are A, written in native machine code, B, are based on IEnumerable and designed to do lazy evaluation, C, use parallel processing techniques and multiple cores, or D, are written in C#. And the answer is B. They're based on IEnumerable and designed to do lazy evaluation. Now let's start working on our first lab exercise, where we'll use the JSON type provider to connect to a remote REST service. So pause the video, do the exercise, and once you've finished it, resume the video, and then we'll review. In this exercise, we're going to connect to a REST service to get some weather data using the JSON type provider. And the JSON type provider allows us to view information about a JSON document. And it uses a sample JSON document to understand the structure of the JSON that's really expected to be used. So let's take a look at using the JSON type provider. So first, in our script file, we'll need to actually make sure that we've got a NuGet reference to the F# data library. So I'm going to add the library in right now. So we'll do a search for F# data. We'll add that in. And we'll just check the version. Awesome. And we'll make sure we're referencing the document using the #R syntax. We'll then add a reference to the F# data namespace, and we'll also add a reference to the system.net namespace because we'll be using the web utility class very soon. So we're opening F# data and also opening up system.net. Now at this point, we'll add in our JSON type provider. And remember, we do need to have a sample JSON document to work with. And so far for this lab, we're using the weather based from a URL in Sydney using the openweathermap.org API. And you can see the structure of the document here. We'll be using this information. So once we're using the type provider, we should have access to things like the coordinate object, the weather object, the main, and many other details from this document as well. So let's copy that reference. We'll go back into Xamarin Studio. And we'll define the type provider. So we're going to define the type, weather equals, and we're going to use the JSON provider. And then we're going to put in that reference document. And then we'll add the function to display the weather for the city by swapping Sydney for another location. So here we're going to write our display weather function. And we'll pass in the city. And at this point as well, we need to make sure we've got the encoded city, mainly because we're passing it as part of a URL. So we need to make sure we're doing the appropriate URL encoding of the city name, because it might have a space in it. So something like New York would have a space. So we'll use the web utility URL encode function and pass in the city. So there's our encoded city. And then we can get the info. And this is going to be from the weather entry based on the JSON type provider. And we're going to load the data based on that very similar URL. So we'll copy the core part of that URL and then add in the encoded city. And there's our data. Then once we have the data, then we can start using the information. So here we're going to use the info and actually investigate the structure by looking at the various data elements that we can directly code against. So you can see we've got the base, the clouds, the coordinate. We should have the main. There we are, the name, and lots of other details as well. There's the weather information too. So let's finish off the function by writing out the code using that info object. So we're going to look at the forecast, and we'll use the name of the data coming back. And there we'll use the info.name, which should be a string, and then info.weather. And it's an array, so we'll get the first element, and then we'll get the main weather there. And then after that, we'll just display the temperature forecast. And then we'll display the details. So we'll use the floating point display, just with one decimal place. And we'll display the minimum weather and also the maximum weather too. And we'll supply the details. So info main, and then we should have the temperature, followed by info main and the temperature minimum. And lastly, info main temp max. Awesome. And then at that point, we just need to display the function. So we can call display weather and then pass in the city we want. So we're going to use New York as the example. And then we'll go ahead, select that code, and then run it in F# Interactive. There we have it. The forecast for New York today is clouds. The temperature forecast is 293.9 with a min of 290.2 and a maximum of 296.2. So that does look a little bit odd. And you would have actually read in the exercise that the temperature data is displaying in Kelvin. So we'll need to change the values we're getting back to something like Fahrenheit or Celsius. So let's actually write a quick function to convert it from Celsius to convert it. Let's write a quick function to convert values from Kelvin through to Fahrenheit. And we'll pass in the Kelvin amount, and that will really be the float value. We'll make sure it's a float. Multiply it by 9 as a double, divide it by 5 as a double, and then subtract 459.67, the standard mechanism we use. So there we'll just convert our values. So when we're using temperatures, we'll just pass the appropriate function in. Okay, so this time when we run the code in F# Interactive, we should see the temperatures in Fahrenheit instead. And that's a really good outcome. Now, if you did the additional exercise, you would have noticed that we had an additional version where you got to use the awesome F# feature of units of measure. So let's actually just quickly open up that document and review what's going on. And you can see here we've actually defined units of measure of Kelvin, Celsius, and also Fahrenheit. And we've also added conversion routines. And you'll note that when we get the values from the REST service as well, we're also converting them to Kelvin, and then we're actually passing them into the appropriate conversion technique. So we've got to convert Kelvin to Celsius, but we could also swap that out to convert Kelvin to Fahrenheit as well. So we're getting the values back, we're multiplying them by 1 as Kelvin, just to indicate that these values actually are in fact Kelvin, and then we're passing that Kelvin value into our convert function. And then we're displaying that, and then we're returning those values as the appropriate unit of measure, either Celsius or Fahrenheit. And then we're displaying the information using the floating point value part of the unit of measure. So let's actually quickly run this. And you can see the effects that we're getting here. So this is in Celsius. The details for today is 20.9 degrees Celsius with a minimum of 17.2 and a maximum of 23.2. So that concludes our first objective, where we've had a look at type providers, we've defined what they are, we've had a look at some of the benefits of type providers, and also gone through an exercise outlining how to connect to type providers too and access the data. So now that we've got the basics of type providers down, let's look at how we shape the data coming from the provider. First, remember that type providers return sequences, and these are enumerable, read-only data structures that are part of F#. And since the returning data is just a standard F# sequence, you can use all the normal sequence operations to filter, project, and transform the data. Here, for example, we're consuming the World Bank provider and retrieving all the countries with a population over 1 million people in 2012 by first creating a tuple with a country and population, and then filtering that sequence down to just the ones that we're interested in. And in this case here, we're chaining methods together using the pipeline operator, so that as we read a country from the provider, we're generating a single tuple and then feeding that to the filter where it's either discarded or added to the final resulting list. So while we can use sequence operations, it turns out there's a much better way to query the data, and that's using LINQ, the language integrated query support. And this is exposed in F# using query expressions. And query expressions enable you to query a data source and put the data in a desired form. And it starts with the query keyword. And this tells F# that the body, held within the curly braces, is a query expression. And queries work on sequence data, anything IEnumerable. And typically the way we feed data into a query is through a loop expression. And for example, here we use the for-in-do loop to process all the countries from the World Bank provider. And we can then provide a projection and indicate what return data elements we want from the query. This is done using the select keyword, just like a LINQ in C#. And here we're creating a tuple with the name of the country and the income share of the lowest 10% of the population in 2010. Finally, we often provide some kind of filter for the data, and this is done using the where keyword, again, just like C#'s LINQ implementation. And the provided filter must be a single expression. So you can see here we surround the expression with parentheses, since we're combining two expressions with the pipelining operator. And in this code example here, we want to ignore countries that don't have the data we need. And in that case, the income share will be not a number. And here we provide a filter to use the system double is not a number static method, run it through the not operator, and then use that result as our expression result. And there are a number of other operators we can apply to query expressions, most of which are pretty intuitive and familiar if you've used LINQ in C#. For example, we can restrict our result set to items that contain a specific parameter. We can get a count of the results, sort them, average them, or even create inner and outer joins. And this is a very small sampling of all the operators available, and MSDN has extensive documentation on the available operators, which you should check out for more information. And here's a quick example of using some of the additional operators. Here, we'll take all the countries where the name starts with C, is in Europe, sorted by name, and we skip the first result and then take the next 5. And these queries we're building are actually expression trees that work on a supplied set of data. However, these expressions are not actually executed until you consume the query. In other words, you have to pipe the query into a sequence operation or use a loop across the query to actually get it to do anything. As an example, here we take our filtered income query, we create a list from it using the sequence to list, and then pull the 2 boundary values from the list by grabbing the second value from the tuple. So keep this logic in mind as we do the lab exercise next. Let's do another individual lab exercise where we'll use the World Bank type provider and get some practice writing a query expression. So just like before, pause the video, do the exercise, and once it's completed, resume the video and we can review the exercise. So let's have a review of the World Bank type provider example. And we're going to look for the countries in this example that have the lowest and highest values for the income share held by the highest 10% indicator. And like the previous exercise, we have the F# data added to the project via NuGet. We've added the reference using the #r syntax in our script file, as well as opening up the F# data namespace. Now for the World Bank data, we use the get data context to get access to the information. And we're then using the query expression to filter the results, so we're getting the list of countries and only their income held by the highest 10% and only those columns. And then you can see we're actually returning those 2 elements, the name and that particular indicator, for the year 2010 as a tuple. And you'll notice that the filtered income list is not accessing the data at this point. It's actually not until we call the code at the various sequence calls, the sequence min by and the sequence max by, that we're actually getting a result because we're using that data. So let's run the code in the REPL and we'll see the output. And there you can see the data coming back. The minimum income share is from Slovenia and the maximum income share is from Zambia. So let's finish today's class off with a quick flash quiz. Question 1. Query expressions enable what in F#? Is it SQL expressions, file I/O, type providers, or link? And the answer is link. Question 2. Which of the following is the correct way to write the function below? Is it option A, option B, neither A or B, or are both options correct? And the answer is D. Both options are correct. Question 3. Which statement is true about query expressions? A. Query expressions are triggered using the select keyword. B. Are an example of when loops are useful in F#. Or C. Allow you to filter but not transform data. And the answer is B, are an example of when loops are useful in F#. So congratulations on working through the second objective of today's class. And we've had a look at the query expressions in this class, but overall, we've had a look at the type providers, we've had a look at the benefits of type providers, and there's many. And we've also had a few examples and lab exercises on how to connect to type providers, as well as looking at the link support in F# with query expressions. So that concludes our video on type providers in F#. My name's been Glenn Stevens, and thank you for watching these videos on F# from Xamarin University.